So here's something you probably haven't thought about today, even though it's been keeping you alive since the moment you woke up. The building you're in right now, the walls around you, the ceiling above your head, the floor underneath you, none of that is just sitting there. It's working. Right now, as you lie there, every beam and joist and nail and bolt in this structure is under stress, carrying load, pushing and pulling against its neighbors in a silent, invisible tug-of-war that never stops. The roof is pushing down, the walls are pushing back. The foundation is spreading that weight into the ground beneath it, and the ground is pushing up with an equal and opposite force, because that's how the universe works. If any one of those forces got out of balance, if the ground suddenly couldn't support the weight, or a wall buckled or a beam snapped, you'd know about it very quickly, and not in a good way. But it doesn't happen. It almost never happens. And the reason it almost never happens is engineering. And that's what we're going to talk about tonight. Engineering. The whole wonderful, confusing, occasionally terrifying business of figuring out how to build things that don't fall down, don't blow up, don't collapse, don't flood, don't break in half, and don't kill anyone. We're going to take it nice and slow. Start from the very beginning and just wander through the story of how humans learned to build the world you live in. No rush. If you drift off somewhere along the way, that's perfectly fine. Honestly, engineering is one of those subjects that gets more interesting the more relaxed you are, because it's really about noticing things, noticing forces, noticing patterns, noticing the way materials behave when you push them, and a quiet mind notices things a busy mind doesn't. Let's start with something simple, a force. What even is a force? You feel forces all the time. Gravity is pulling you into your mattress right now. That's a force. Your mattress is pushing back up against you. That's another force. If those two forces are equal, which they are, you stay put. You don't accelerate through the mattress, and you don't float up toward the ceiling. You just lie there, perfectly balanced, perfectly still. Engineers call this equilibrium, and it's maybe the most fundamental idea in all of structural engineering. If something isn't moving, all the forces acting on it must add up to zero. Every push has an equal and opposite push somewhere else. Every pull is balanced by a pull in the other direction. That's Newton's third law, and it's the bedrock that everything else is built on. Now, here's where it starts to get interesting, because forces don't just push straight down and straight up. They flow through structures, like water flows through a network of pipes. When you put weight on one end of a beam, that force doesn't just stay at one end. It travels through the material, spreading out, changing direction, eventually reaching the supports at either end and flowing down into the ground. And the path that force takes, the way it moves through the structure, determines whether the thing stands or falls. Understanding that path, really understanding it, being able to predict it and design for it, that's what structural engineering is. And humans have been doing this for a very, very long time. Not always with math, not always with science, sometimes just with intuition and experience and a willingness to try things and see what happens. Because here's the thing, for most of human history, engineering was not a science. It was a craft, a tradition. You learned by watching someone who'd learned by watching someone else. The Romans built aqueducts that still stand after 2,000 years, and they did it without any formal understanding of the math behind structural mechanics. They didn't know about stress tensors or moment diagrams or elastic modulus. They knew what worked. They knew what shapes were strong. And most importantly, they knew what had fallen down before, and they didn't do that again. But let's go even further back, because the story of engineering really starts with stone. Think about the oldest large structures humans ever built. The pyramids of Egypt. And I know, everyone talks about the pyramids, but here's what I want you to actually think about for a second. The Great Pyramid of Giza was built around 2560 BCE. That's over 4,500 years ago. It contains roughly 2.3 million stone blocks, each one weighing an average of about 2.5 tons, some of them as heavy as 80 tons. The base covers 13 acres. It was the tallest structure on Earth for nearly 4,000 years. Think about that. 4,000 years, nothing taller. And it was built without wheels, without iron tools, without pulleys as we know them, without any of the machinery that we would consider essential for a construction project today. And yet it's still there. It's barely eroded. The base is level to within about 2 centimeters across its entire width, which is roughly 230 meters. That's an astonishing degree of precision for any era, let alone for a civilization working with copper tools and stone hammers. How did they do it? Honestly, we don't know every detail, and that drives some people crazy. But what we do know is fascinating. They understood the most basic engineering principle of all. A wide base supports a heavy load. The pyramid shape is, structurally speaking, about the most stable shape you can build. All the weight flows downward and outward, always in compression. That means the stones are being squeezed, not pulled. And stone is phenomenal in compression. You can stack an enormous amount of weight on stone and it'll hold. What stone is terrible at is tension, pulling. Try to stretch a piece of stone and it cracks almost immediately. The Egyptians didn't know the word compression or tension, but they understood the concept because they'd spent centuries building things and watching what worked and what crumbled. And this right here is the first big confusing idea in engineering that a lot of people never really think about. Compression and tension. Every structure in the world, every bridge, every building, every dam, every airplane wing, is dealing with these two forces. Compression is squeezing, pushing something together, like squishing a marshmallow between your hands. Tension is pulling, stretching something apart, like pulling on a rubber band. And different materials handle these two forces very differently. Stone and brick and concrete are champions of compression. You can pile enormous weight on them and they'll hold, but they're awful in tension. They crack, they snap, they crumble. Wood is decent at both, which is why it was such a useful building material for thousands of years. Steel is extraordinary at both. It can handle enormous compressive forces and enormous tensile forces, which is why steel changed everything when it arrived. But we'll get to that. The reason this matters, the reason compression and tension are so fundamental, is that most of the interesting engineering problems come down to this. How do you take the loads, the weight, the wind, the traffic, the earthquakes, the snow on the roof, the water behind the dam, and channel all of those forces into paths where your material is strong, and keep them away from paths where your material is weak? That's the game. That's really the whole game. And the earliest engineers, the ones who figured it out first, solved it with one of the most elegant shapes in all of architecture, the arch. The arch is one of those things that seem so simple, so obvious, that you might not realize how revolutionary it was. Here's the problem it solves. If you want to span an opening, a doorway, a window, a gap between two walls, the simplest way is to lay a flat stone across the top. That's called a lintel, and it works fine for small openings. But here's the problem with lintels. A flat stone spanning a gap is in bending, and bending creates tension on the bottom face of the stone. The top of the stone is being compressed, squeezed, but the bottom is being stretched. And as I just said, stone is terrible in tension, so a flat stone lintel can only span a limited distance before the tension on the bottom face causes it to crack and break. This is why the doorways in ancient stone buildings are relatively narrow. You can only stretch a stone lintel so far. The arch solves this brilliantly. Instead of a flat beam, you arrange wedge-shaped stones, called voussoirs, in a curve. The keystone goes in at the top, locking everything together. And here's the beautiful thing. In a properly shaped arch, every single stone is in pure compression. The weight from above pushes down on the keystone, which pushes outward on the stones beside it, which push outward on the stones beside them, and so on, all the way down to the base. The force flows through the curve of the arch entirely, as compression, squeezing each stone against its neighbors. There's no tension anywhere. And since stone is brilliant in compression, the arch can span much, much farther than a flat lintel ever could. The Romans didn't invent the arch. The Mesopotamians and Etruscans used arches before them. But the Romans turned the arch into one of the most powerful engineering tools in history. They used arches to build bridges, aqueducts, amphitheaters, triumphal monuments, and some of the largest enclosed spaces the ancient world had ever seen. The Pantheon in Rome, built around 125 CE under Emperor Hadrian, has a concrete dome, which is essentially a three-dimensional arch, an arch rotated around its center, that spans over 43 meters. It was the largest unsupported dome in the world for over 1,300 years. And it's still standing, still intact. You can walk in there today, look up, and see the same coffered ceiling that Romans saw 19 centuries ago. The oculus, the open hole at the top of the dome, is still open to the sky. When it rains, rain falls through it onto the slightly convex marble floor, which is subtly graded to drain the water away. The whole thing is a masterpiece of engineering, and it was built with a type of concrete that we only recently figured out was actually superior to modern concrete in certain ways. The Romans mixed their concrete with volcanic ash, pozzolana, which creates a chemical reaction with seawater that actually makes the concrete stronger over time. There are Roman harbor structures that have been submerged in salt water for 2,000 years and are harder now than when they were built. Modern Portland cement concrete, by contrast, would be corroded and crumbling after a few decades in the same conditions. But here's the thing about the Romans, and this is where the story takes a turn that reveals something important about how engineering actually progresses. The Romans were brilliant builders. Their roads, their aqueducts, their concrete, all extraordinary. But they were engineers in the empirical sense, the trial and error sense. They didn't have a theoretical framework for understanding why their structures worked. They didn't calculate stresses or analyze forces. They built things that looked like things that had worked before, and they made them bigger and thicker and heavier to be safe. Their approach was, essentially, overbuild everything. Use more material than you probably need. Make the walls thicker, the columns fatter, the foundations deeper. And when something did fail, learn from it and don't do that again. This worked. It worked remarkably well, but it had limits. Without a theoretical understanding of forces and materials, you can't optimize. You can't make things lighter or more efficient. You can't predict how a new shape or a new material will behave without actually building it and seeing what happens. And for most of human history, that was fine. Stone and brick and timber were the materials. Arches and columns and thick walls were the shapes. And everything was heavy and solid and massively over-engineered. But eventually, and this is the story of the last few hundred years, engineers started wanting to build things that couldn't be over-engineered. Things that needed to be light, or long-spanning, or tall, or flexible. Things where you couldn't just pile on more material and hope for the best. And that's when engineering had to become a science. That's when people started doing math, and the person who arguably started that transformation, the person who first applied serious mathematical analysis to the problem of how structures carry loads, was a man you've probably heard of in a completely different context. Galileo Galilei. Yes, the same Galileo who pointed his telescope at Jupiter and got in trouble with the Pope. In 1638, near the end of his life, under house arrest for his astronomical heresies, Galileo published a book called Two New Sciences, and one of those new sciences was what we'd now call the strength of materials. Galileo asked a deceptively simple question. Why can't you just scale things up indefinitely? Why can't you build a ship 10 times bigger by making every piece 10 times larger? Why does a large animal need proportionally thicker bones than a small one? And his answer was the beginning of engineering science. He showed that when you scale something up, the strength of a beam, which depends on its cross-sectional area, grows as the square of the scaling factor, but the weight, which depends on its volume, grows as the cube. Double the size, and the beam is 4 times stronger, but 8 times heavier. Triple the size, and it's 9 times stronger, but 27 times heavier. The weight wins. Eventually, if you keep scaling up, the structure collapses under its own weight. That's why you can't just build an ant the size of a house. Its legs would snap. And it's why engineers need to be clever about shapes and materials rather than just making things bigger. That insight, that you can't just scale things up, that there are fundamental relationships between size and strength and weight, is one of the most important ideas in engineering. And it was just the beginning. Over the next 2 centuries, mathematicians and natural philosophers would develop the tools that modern engineering is built on. Robert Hooke, in 1678, discovered that materials deform proportionally to the force applied. Stretch a spring twice as hard, and it stretches twice as far. That's Hooke's law, and it's the foundation of elasticity theory. Leonhard Euler, in the 18th century, worked out the mathematics of how columns buckle under compressive load. A slender column doesn't just crush, it bows sideways and snaps, and Euler figured out exactly how much load it takes to trigger that buckling, based on the column's length and stiffness. Claude Louis Navier, in the early 19th century, developed beam bending theory, giving engineers the equations to calculate exactly how a beam deflects under load and where the maximum stresses occur. And all of this, Galileo's scaling laws, Hooke's elasticity, Euler's buckling, Navier's beam theory, all of it was coming together just in time for the biggest revolution in engineering history, because by the late 18th century, something new was entering the world, a material that would change everything. A material that was strong in both compression and tension, that could be shaped and formed and joined, that was lighter than stone and stronger than wood, that could span distances and carry loads that no previous material could match. That material was iron, and then, not long after, its even more remarkable descendant, steel. And the story of what engineers did with iron and steel, the structures they suddenly dared to imagine, the bridges and towers and buildings that leapt from impossible to inevitable in a single generation, that story starts in a valley in central England, in a place called Coalbrookdale, where a Quaker ironmaster named Abraham Darby had figured out something that would reshape the world. See, iron had been around for thousands of years. Humans had been smelting iron since at least 1200 BCE. But for most of that history, making iron was a small-scale, expensive, unreliable process. You'd heat iron ore with charcoal in a small furnace, and you'd get a spongy lump of wrought iron that you'd have to hammer and fold and hammer again to squeeze out the impurities. It worked, but it was slow, and the pieces you could make were limited in size. You could make swords, nails, horseshoes, tools, but you couldn't make structural beams or bridge components, not at any useful scale. What Darby figured out in 1709 was how to smelt iron using coke. That's coal that's been heated to drive off the impurities, instead of charcoal. This doesn't sound like a big deal, but it was enormous. Coal was abundant and cheap in England. Charcoal required wood, and England was running low on forests. Switching to coke meant you could build much bigger furnaces, run them continuously, and produce vastly more iron at a fraction of the cost. It took decades for the process to be refined and scaled up, but by the late 18th century, iron was becoming available in quantities and sizes that had never been possible before. And that changed what engineers could imagine. The first major structure to be built entirely of iron was the Iron Bridge, spanning the River Severn at Coalbrookdale itself, completed in 1779. It was designed by Thomas Farnells Pritchard and built by Abraham Darby III, the grandson of the original coke-smelting Abraham Darby. And here's what's fascinating about it. The bridge was built like a piece of carpentry. The iron ribs are shaped and joined using the same techniques you'd use with timber: mortise and tenon joints, dovetails, wedges. The builders didn't yet have a vocabulary for iron construction, so they used the vocabulary they knew. It's like watching someone write their first email in the style of a formal letter. The new medium, but the old habits. The bridge still stands, by the way. You can walk across it today. It's been carrying pedestrians for nearly 250 years. But the Iron Bridge, beautiful as it was just the opening act. Because once engineers had iron in quantity, they started doing things that would have been unthinkable with stone or wood. And the first great arena for these new ambitions was bridges. Because bridges are, in some ways, the purest expression of structural engineering. A bridge has one job: get something across a gap. And the gap doesn't care about your feelings. It's a fixed distance, and you have to span it. The forces are clear: gravity pulling down, the supports pushing up, and whatever you're carrying, people, horses, carts, eventually trains, adding to the load. A bridge is a structural problem stripped to its essence, and solving it elegantly has obsessed engineers for centuries. Now, let me walk you through the basic types of bridges, because once you understand them, you'll never look at a bridge the same way again. And they all come back to that fundamental idea we talked about: compression and tension, and routing forces through paths where your material is strong. The simplest bridge is a beam bridge. It's exactly what it sounds like: a horizontal beam or slab resting on supports at each end. Think of a log laid across a stream. That's a beam bridge. The weight on the beam creates bending, and bending means the top of the beam is in compression, being squeezed, while the bottom is in tension, being stretched. This is really important, so let's sit with it for a second. Picture a beam bending under a load. The top surface is getting shorter. It's being compressed, squished together. The bottom surface is getting longer. It's being stretched, pulled apart. Somewhere in the middle, there's a line where the material is neither compressed nor stretched. Engineers call that the neutral axis. And the farther you get from that neutral axis, the closer you get to the top or bottom surface, the higher the stress. That's why I-beams, those steel beams shaped like the letter I that you see in construction, have that particular shape. All the material is concentrated at the top and bottom, the flanges, where the stresses are highest. The thin web in the middle just holds the flanges apart. You don't need much material there, because the stress is low. It's an incredibly efficient shape. Maximum strength, minimum weight. That's engineering at its most elegant. But beam bridges have a limit. As the span gets longer, the bending forces get more intense, and you need a deeper, heavier beam to resist them. For really long spans, beam bridges just become impractical. So engineers turned to other shapes, and one of the most important was the truss. A truss is essentially a framework of triangles. Take some straight bars, iron rods, wooden planks, steel tubes, whatever, and connect them at their ends to form triangles. Here's why triangles are so special in engineering. A triangle is the only polygon that can't be deformed without changing the length of its sides. Think about a square made of 4 rods connected by pins at the corners. You can push on one corner and collapse the whole thing into a diamond shape without bending any rod. The corners just rotate. It's unstable. But a triangle? Try to deform a triangle made of rigid rods and you can't. The shape is locked. It's inherently rigid. And when you load a triangle, the forces in each member are purely axial, meaning the bars are either being pulled straight apart, tension, or pushed straight together, compression. There's no bending, and that's incredibly efficient because materials handle straight tension and straight compression much better than bending. So a truss bridge takes this principle and runs with it. You build a framework of triangles, and the load from the bridge deck gets distributed through this triangular network, with each bar carrying either pure tension or pure compression. The result is a bridge that can span much farther than a simple beam, using much less material. And if you've ever driven across a bridge with those distinctive crisscrossing steel members above and beside you, that lattice-like framework, that's a truss. The Pratt truss, the Warren truss, the Howe truss. These are all variations on the same idea, just with the triangles arranged in different patterns to optimize the force distribution. Now, trusses are wonderful, but for really long spans of hundreds of meters or more, you need something even more ambitious. And this is where suspension bridges come in. And honestly, suspension bridges are one of the most beautiful ideas in all of engineering. Here's the concept. Instead of trying to make a beam or truss strong enough to span a huge gap, which means fighting bending forces that grow enormous over long distances, you hang the bridge deck from cables. The cables go up and over tall towers, and they're anchored at both ends to massive blocks of concrete or rock called anchorages. The weight of the deck and everything on it pulls the cables downward, and the cables transmit that force as pure tension to the towers and anchorages. The towers are in compression. They're being pushed down by the cable tension. The anchorages are being pulled inward by the cable ends, and the cables themselves are in pure tension. They're just being pulled. No bending, no shear. Just straight pull. And here's the beauty of it. Cables are incredibly efficient in tension. A steel cable can carry enormous tensile loads relative to its weight. You can hang a bridge deck from cables over a span that would be completely impossible for a beam or truss. The main cables on a major suspension bridge are themselves engineering marvels. They're not single strands, but bundles of thousands of individual wires, each one carefully laid parallel to the others, bound together into a cable that might be a meter in diameter and contain over 26,000 individual wires. The main cables on the George Washington Bridge in New York, for instance, each contain 26,474 individual steel wires. And the person who more than anyone else pioneered the modern suspension bridge, the person who proved that this idea could work at a scale nobody had imagined, was a German-born American engineer named John Augustus Roebling. And his story is one of the great dramas of engineering history, because it involves genius, tragedy, and one of the most famous structures on Earth. Roebling was born in 1806 in Mühlhausen, Germany. He studied engineering at the Royal Polytechnic Institute in Berlin, where he actually attended lectures by the philosopher Georg Wilhelm Friedrich Hegel, which is a strange and wonderful detail. The builder of the Brooklyn Bridge, studying under one of the most abstract philosophers who ever lived. Roebling emigrated to America in 1831, tried farming in western Pennsylvania, hated it, and eventually found his calling in engineering. He started a wire rope manufacturing business, which turned out to be perfectly positioned for the coming age of suspension bridges, because wire rope is exactly what you need to build suspension cables. Roebling built several suspension bridges that were groundbreaking for their time. His Niagara Falls suspension bridge, completed in 1855, was the first suspension bridge strong enough to carry railroad trains. People had said it couldn't be done, that a suspension bridge would sway and flex too much under the dynamic loads of a locomotive. Roebling proved them wrong by adding diagonal stays and stiffening trusses that controlled the movement of the deck. He understood something that many of his contemporaries didn't. A suspension bridge needs to be stiff as well as strong. It's not enough to hang the deck from cables and hope for the best. You need to control how the deck moves, especially in wind, and that understanding would prove to be prophetic, as we'll see later when we talk about one of the most spectacular bridge failures in history. But for now, let's stay with Roebling, because in 1867 he began work on his masterpiece, the Brooklyn Bridge. The Brooklyn Bridge. Just think about what that project meant. In the 1860s, Brooklyn and Manhattan were separate cities, separated by the East River. Hundreds of thousands of people crossed that river every day by ferry, and in winter, ice could shut the ferries down for weeks. A bridge was desperately needed, but the East River at that point is over 1,600 feet wide, nearly 500 meters, with a deep, fast-moving channel that made it impossible to build piers in the middle. Any bridge would need a single clear span, longer than anything that had ever been built. And it would need to be high enough above the water, at least 135 feet, about 41 meters, to let the tall-masted ships of the era pass beneath it. Roebling's design was audacious: 2 massive stone towers, each about 276 feet tall, about 84 meters, rising from caissons sunk to bedrock at the bottom of the river. 4 main cables, each nearly 16 inches in diameter, draped over the towers and anchored in enormous stone anchorages on each shore. A roadway deck suspended from the cables by a web of vertical suspenders and diagonal stays. When completed, it would be the longest suspension bridge in the world by a wide margin, and those stone towers would be the tallest structures in the Western Hemisphere. And then, tragedy. In June 1869, while surveying the site for the Brooklyn Tower, Roebling was standing on a dock when an arriving ferry crushed his foot against a piling. His toes were amputated, but he developed tetanus, lockjaw, from the injury. 3 weeks later, he was dead. He was 63 years old. The man who designed the Brooklyn Bridge never got to build it. But here's where the story takes a remarkable turn. John Roebling's son, Washington Roebling, took over as chief engineer. Washington was 32 years old. He'd studied engineering at Rensselaer Polytechnic Institute, served with distinction as a Union officer in the Civil War. He was at Gettysburg, and he'd worked alongside his father on previous bridge projects. He knew the design inside and out, and he dove into the construction with total commitment. The hardest part of building the Brooklyn Bridge was sinking the caissons, the foundations for the 2 great towers. A caisson is essentially a giant upside-down wooden box, open at the bottom, that's sunk to the riverbed. Compressed air is pumped in to keep the water out, and workers go inside, down through airlocks, into the pressurized chamber, and dig out the mud and rock at the bottom, allowing the caisson to sink deeper and deeper under the weight of the masonry being built on top of it. It's like pushing an inverted cup into a tub of water and digging out the sand at the bottom. The conditions inside the caissons were nightmarish. The air was hot, humid, and pressurized. The workers labored in dim candlelight, knee-deep in mud, chipping away at boulders with hand tools. And many of them got sick with a mysterious condition. Excruciating joint pain, paralysis, sometimes death, that struck when they came back up to the surface. They called it the bends, or caisson disease. We now know it as decompression sickness. The high-pressure air forced nitrogen gas into the workers' blood and tissues, and when they returned to normal pressure too quickly, the nitrogen came out of solution and formed bubbles in their joints, their spinal cords, their brains. It's the same thing that happens to scuba divers who ascend too quickly. But in the 1870s, nobody understood the mechanism. They just knew that men went down healthy and came up crippled. Washington Roebling himself was one of the victims. He spent so much time in the caissons, supervising the work, that he developed a severe case of decompression sickness that left him partially paralyzed, nearly blind, and in chronic pain. By 1872, he could no longer visit the construction site. For the remaining 11 years of construction, he directed the work from his bedroom in a house overlooking the bridge site, watching through a telescope and sending detailed instructions through his wife, Emily Warren Roebling, who became, in practice, the day-to-day supervisor of the project. And Emily Roebling is one of the unsung heroes of engineering history. She taught herself higher mathematics, materials science, stress analysis, cable construction, everything she needed to understand the bridge's engineering, so she could serve as the intermediary between her husband and the construction crews and the board of trustees. For over a decade, Emily was the face of the Brooklyn Bridge project, negotiating with contractors, defending design decisions to politicians, solving technical problems on the fly. When the bridge was finally opened on May 24, 1883, 14 years after construction began, Emily Roebling was the first person to cross it, carrying a rooster as a symbol of victory. The Brooklyn Bridge was a sensation. Over 150,000 people crossed it on its opening day. It was the longest suspension bridge in the world, the first to use steel wire for its cables instead of iron, and its Gothic stone towers became instant landmarks, symbols of American ambition and engineering prowess. It transformed New York City, linking Brooklyn and Manhattan in a way that eventually led to their consolidation into a single city in 1898. And it demonstrated something profound about suspension bridge design, that this type of structure could span enormous distances, carry heavy loads, and last for generations. The Brooklyn Bridge is still in use today, still carrying traffic across the East River, over 140 years after it opened. The cables Roebling designed, the towers his workers built in those terrible caissons, the whole magnificent structure, still working, still in equilibrium, still balancing compression and tension, just as it was designed to do. But the story of bridges doesn't end with triumph, because engineering is also a story of failure, and sometimes the failures teach more than the successes. And there's one bridge failure in particular that every engineering student learns about. A failure so dramatic, so visually unforgettable, that the footage of it has become one of the most famous pieces of engineering film ever recorded. It happened on November 7, 1940, in the state of Washington, over a body of water called the Tacoma Narrows. And what happened that day changed the way engineers think about every structure they would ever design for the rest of their careers. The Tacoma Narrows Bridge had opened just 4 months earlier, on July 1st, 1940. It was a suspension bridge, about 5,939 feet long overall, with a main span of 2,800 feet, crossing a windy strait in Puget Sound. And from the very first day it was open, the bridge moved. Not just a little, a lot. In moderate winds, the deck would rise and fall in gentle undulations, like a ribbon waving in the breeze. People who drove across it said it felt like riding a roller coaster. The construction workers had nicknamed it Galloping Gertie long before it opened, because even during construction, the deck had this strange, rhythmic bounce. Local people actually drove out of their way to cross it because the ride was so unusual. It was a novelty, an amusement. Nobody was amused on November 7th. That morning, a steady wind of about 42 miles per hour, not an extreme wind, not a hurricane, just a strong, steady breeze, hit the bridge, and the bridge started moving differently than it had before. Instead of the gentle vertical bouncing that people had gotten used to, the deck began twisting. One side would rise while the other dropped. Then they'd reverse, back and forth, the entire deck rotating along its length like a corkscrew. The twisting grew more and more violent. The amplitude increased with every cycle. Cars were abandoned on the deck as people fled on foot, crawling on their hands and knees because the deck was pitching so wildly they couldn't stand. A newspaper photographer named Barney Elliott and his colleague captured the event on film. Grainy, black and white footage that has become one of the most watched engineering films of all time. At 11 o'clock in the morning, after roughly an hour of this violent twisting, the bridge tore itself apart. Sections of the concrete deck broke free and fell into the water 600 feet below. The main span collapsed. The only casualty was a cocker spaniel named Tubby, trapped in an abandoned car on the deck, who bit a rescue worker trying to save him and went down with the bridge. Everyone else made it off in time. Now, here's what's really important about this failure, and it's actually one of the most misunderstood events in engineering history. For decades, textbooks explained the Tacoma Narrows collapse as a case of resonance, the idea being that the wind happened to push the bridge at exactly its natural frequency, the same way you can push a swing at just the right rhythm to make it go higher and higher. And resonance is a real phenomenon that engineers absolutely need to worry about. Every structure has natural frequencies, specific rates at which it naturally wants to vibrate, like a tuning fork vibrating at a specific pitch. If an external force pushes at that same frequency, the vibrations build up, getting bigger and bigger with each cycle. That's resonance, and it can be devastating. But the Tacoma Narrows collapse wasn't actually simple resonance. The wind that day was steady, not pulsing rhythmically. More recent analysis points to a phenomenon called aeroelastic flutter. Here's what that means. When wind flows over a bridge deck, it creates aerodynamic forces, lift and drag, similar to what happens with an airplane wing. If the bridge deck twists slightly, the angle of the wind changes, and the aerodynamic forces change too. And under certain conditions, the change in forces actually reinforces the twist. It pushes the deck further in the direction it's already moving. The deck twists more, which creates even stronger reinforcing forces, which twist it even more. It's a feedback loop, a self-reinforcing cycle of energy transfer from the wind into the structure, feeding on itself, growing with every oscillation until the structure can't take it anymore. And the reason the Tacoma Narrows Bridge was susceptible to this, while other suspension bridges weren't, comes down to its design. The bridge was extraordinarily slender for its length. The ratio of the deck depth to the span length was about 1 to 350, meaning the deck was very, very shallow relative to how far it had to span. And instead of an open truss structure that would let wind pass through, it used solid plate girders along the sides of the deck, essentially flat walls of steel that caught the wind like sails. The designer, Leon Moisseiff, was a brilliant and highly respected engineer who had worked on the Manhattan Bridge and consulted on the Golden Gate Bridge. He'd been pushing for more elegant, more slender bridge designs, influenced by a theory called deflection theory that suggested suspension bridges could be made much lighter and more flexible than traditional practice allowed. And, in a narrow engineering sense, he was right. The Tacoma Narrows Bridge was structurally adequate for the loads it was designed to carry. What Moisseiff didn't adequately account for was aerodynamics. He didn't model how the wind would interact with that shallow, flat-sided deck. Nobody did, because in 1940, the science of aeroelasticity as applied to bridges simply didn't exist yet. And that, right there, is one of the most important lessons in all of engineering. You can get the structural calculations right, the forces, the stresses, the material strengths, and still fail catastrophically because you didn't think about the right problem. Moisseiff solved the structural problem correctly, but the Tacoma Narrows Bridge didn't fail as a structure. It failed as an aerodynamic body. The disaster forced the entire profession to reckon with wind dynamics in a way they never had before, and today, every major bridge design includes extensive wind tunnel testing and computational fluid dynamics analysis. The Tacoma Narrows collapse taught engineers that structures don't just carry loads, they interact with their environment, and that interaction can be deadly if you don't understand it. The current Tacoma Narrows Bridge, by the way, the replacement, completed in 1950, is much deeper, much stiffer, and uses open trusses instead of solid plate girders, allowing wind to pass through rather than catching it. It doesn't gallop, it doesn't twist, it just sits there, doing its job, quietly and reliably, the way a good bridge should. Now, let's shift gears a little. We've been talking about bridges, and bridges are a wonderful way to understand forces. But there's another type of structure that changed the world even more dramatically, that reshaped cities, transformed economies, and created the skyline that defines the modern age: skyscrapers. And the story of how we learned to build tall is, in its own way, just as dramatic as the story of bridges, and it revolves around three inventions that all had to come together at the same time. The first is structural steel. The second is the elevator. The third is the steel frame. And without any one of these three, the skyscraper as we know it simply couldn't exist. Let's start with steel, because steel is one of the most important materials in human history, and the story of how we learned to make it cheaply is one of the great industrial dramas. Iron, as we talked about, was available in large quantities by the late 18th century thanks to coke smelting. But iron has limitations. Cast iron, the kind that comes straight out of a blast furnace, is high in carbon, which makes it hard and brittle. It's strong in compression, but weak in tension, and it can shatter under sudden impact. Think of a cast iron skillet dropped on a hard floor. It might crack or break, because cast iron doesn't bend, it snaps. Wrought iron, which has most of the carbon hammered out of it, is tougher and more ductile. It bends instead of breaking, but it's softer and weaker. What engineers really wanted was something in between. Something with enough carbon to be strong, but not so much that it becomes brittle. Something that could handle both tension and compression. Something that could be bent and shaped without breaking, but that would spring back to its original shape when the load was removed. That something was steel. And people had been making steel in small quantities for centuries. Damascus steel, crucible steel, the legendary blades of Japanese swordsmiths. But it was expensive. Making steel required precise control of carbon content, and the methods available, crucible melting, cementation, could only produce small batches. You couldn't make a bridge out of steel. You couldn't make a building frame. There just wasn't enough of it, and it cost too much. And then, in 1856, an English inventor named Henry Bessemer announced a process that would change everything. The Bessemer process was deceptively simple in concept. You take molten pig iron, the carbon-heavy stuff straight from the blast furnace, and you blow air through it. The oxygen in the air combines with the excess carbon in the iron, burning it off as carbon dioxide. In about 20 minutes, you go from brittle pig iron to mild steel. No fuel needed for the conversion itself. The burning carbon generates its own heat. It was fast, it was cheap, and it could be done on an industrial scale. A Bessemer converter could produce 5 tons of steel in 20 minutes, a process that previously would have taken days. Now, the Bessemer process wasn't perfect. It didn't work well with iron ore that contained phosphorus, which was common in European ores. That limitation was eventually solved by Sidney Gilchrist Thomas and Percy Gilchrist in 1878, who lined the converter with basic, as in alkaline, refractory material that absorbed the phosphorus. And then the open hearth process, developed by Carl Wilhelm Siemens and Pierre-Emile Martin, offered even more precise control of the steel's composition, making it the dominant steelmaking method by the early 20th century. But it was the Bessemer process that broke the dam. Between 1860 and 1900, the price of steel dropped by roughly 80%. What had been a precious specialty material became a bulk commodity, and suddenly, engineers could build with steel. And here's what steel made possible. Steel has a tensile strength roughly 10 times greater than cast iron. It has a compressive strength, comparable to stone, but at a fraction of the weight. A steel column can carry the same load as a stone column that's many times thicker and heavier, and steel can be rolled into standardized shapes, I-beams, channels, angles, that can be bolted or riveted together on site, assembled like a giant erector set. This last point is what made the skyscraper possible, because before steel frames, buildings were built with load-bearing walls. The walls carried the weight, and the taller you wanted to build, the thicker the walls had to be at the base to support all the weight above. The Monadnock Building in Chicago, completed in 1891, is 17 stories tall and is one of the tallest load-bearing brick buildings ever constructed. Its walls at the ground floor are 6 feet thick, 6 feet of solid brick just to hold the building up, and that was about the limit. Go much higher, and the walls at the base would have to be so thick that there'd be hardly any usable space inside. The steel frame changed that equation completely. Instead of the walls carrying the load, you build a skeleton of steel columns and beams, a rigid frame, and the building's weight flows through the steel skeleton down to the foundations. The walls become just a curtain, a skin, hung on the outside of the frame. They keep the weather out, but they don't carry any structural load. This is called curtain wall construction, and it's the basic principle behind virtually every tall building in the world today. The walls aren't holding the building up, the steel frame is. And because steel is so strong relative to its weight, you can build 20 stories, 50 stories, 100 stories, without the columns at the base getting impossibly thick. The building that's usually credited as the first true skyscraper, though there's some debate about definitions, is the Home Insurance Building in Chicago, designed by William LeBaron Jenney and completed in 1885. It was 10 stories tall, about 138 feet, which doesn't sound very impressive by modern standards, but was revolutionary for its time, because it was the first tall building to use a structural steel and iron frame to carry the building's weight. Jenny was a Civil War veteran. He'd served as an engineer on General Sherman's staff, and he'd studied at the prestigious École Centrale des Arts et Manufactures in Paris. He understood the principles, and his building proved the concept. The steel frame worked. The curtain walls worked. You could build tall without building thick. And from there, the race was on. Chicago, after the Great Fire of 1871, was the perfect laboratory, a booming city with enormous demand for commercial space and a blank canvas of burned-out blocks to rebuild on. Engineers like Daniel Burnham, John Root, and Louis Sullivan pushed the boundaries, building taller and taller, developing the Chicago School of Architecture that married structural steel with innovative design. And then New York joined the race, and the competition between the two cities, and eventually between individual buildings, drove engineering forward at a dizzying pace. But building tall wasn't just about the frame. There was another problem, a more practical one, that had to be solved before skyscrapers could work as actual places where people lived and worked. And that problem was vertical transportation. How do you get people to the upper floors? Walking up 10 flights of stairs is manageable if annoying. Walking up 50 flights is effectively impossible for daily commuting. Without a fast, safe, reliable way to move people vertically, a tall building is just a tall monument, impressive to look at, useless to occupy. And that brings us to the elevator, and to a showman's gamble at the Crystal Palace in New York in 1854 that changed the world. Elisha Graves Otis didn't invent the elevator. Hoisting platforms had existed for centuries, pulled by ropes and counterweights, used in mines and warehouses. What Otis invented was the safety elevator, the thing that made people willing to ride in one. Because the problem with early elevators wasn't lifting people up. It was what happened when the rope broke. And ropes broke. They broke regularly. And when the rope on a hoisting platform broke, the platform dropped like a stone, and everyone on it died. Nobody in their right mind would commute to work on one of those things. Otis's invention was a ratchet safety mechanism. He mounted toothed rails on either side of the elevator shaft and spring-loaded catches on the elevator platform. If the rope broke, the catches would snap outward, lock into the teeth of the rails, and stop the platform instantly. Simple, reliable, foolproof. And to demonstrate it, Otis did something brilliant and dramatic. At the Crystal Palace exhibition in New York, he stood on an elevator platform, had himself hoisted high into the air before a crowd of spectators, and then ordered his assistant to cut the rope with an axe. The crowd gasped. The platform dropped a few inches. The safety catches engaged, and Otis stood there, perfectly safe, and reportedly announced, "All safe, gentlemen, all safe." It was one of the great pieces of showmanship in engineering history, and it launched an industry. Within a few years, Otis elevators were being installed in buildings across America. By the 1870s, hydraulic elevators could move smoothly and quickly, up to about 10 or 12 stories. By the 1880s, electric elevators, powered by motors, could go higher and faster. The electric elevator, combined with the steel frame, finally made the true skyscraper possible. You could build tall, and people could get to the top. And then another problem emerged, one that you might not think of immediately, but that turns out to be one of the most critical challenges in tall building design. A problem that gets worse the taller you build, that has destroyed buildings and terrorized occupants, and driven some of the most sophisticated engineering analysis ever performed. That problem is wind. And the story of how engineers learned to deal with wind in tall buildings starts with a building that most people think of as a symbol of ambition and elegance, but that engineers think of as a landmark in the science of wind engineering: the Empire State Building. The Empire State Building was completed in 1931, in the middle of the Great Depression, in what might be the most remarkable construction sprint in history. The steel frame went up at an average rate of about 4.5 stories per week. At its peak, construction was proceeding so fast that the steel was still warm from the foundry when it was being riveted into place on the 86th floor. The whole building, 102 stories, 1,454 feet to the tip of its mooring mast, over 60,000 tons of steel, was built in just 410 days, about 14 months from groundbreaking to opening day. By comparison, modern skyscrapers of similar size typically take 3 to 5 years. But here's the engineering challenge that the Empire State Building's designers had to grapple with, and it's the same challenge that confronts every tall building engineer today: wind. At street level, on a typical day, you might feel a gentle breeze, maybe 10 or 15 miles per hour. Up at the top of a tall building, the wind is much stronger, not just a little stronger, but dramatically stronger, because the boundary layer of the atmosphere slows wind near the ground due to friction with the surface and all the buildings and trees and terrain. As you go higher, you emerge from that boundary layer, and the wind speeds increase significantly. At the top of the Empire State Building, sustained winds routinely exceed 60 or 70 miles per hour, and in storms they can exceed 100. And wind doesn't just push on a building like a steady hand shoving a post. It does something much more complicated and much more dangerous. When wind flows around a tall building, it creates vortices, rotating eddies of air, that shed alternately from one side and then the other, like the swirling patterns you see behind a stick in a stream. This is called vortex shedding, and it creates alternating pockets of low pressure on either side of the building. The building gets pushed one way, then the other, in a rhythmic oscillation, and if the frequency of that oscillation happens to match one of the building's natural frequencies, there's that resonance concept again. The swaying can build up to dangerous levels. Now, the Empire State Building is actually very stiff. Its steel frame is massively robust, partly because it was originally designed with a mooring mast for dirigibles, airships, at the top, which required enormous strength to resist the mooring forces. The building sways only about 1.5 inches in strong winds. You'd barely feel it if you were inside. But as buildings got taller and more slender in the decades after the Empire State Building, wind became a bigger and bigger problem. Consider this: if you double the height of a building, the wind force doesn't just double. It increases dramatically, because wind speed increases with height, and the pressure from wind grows with the square of the speed. And the building's tendency to sway increases even faster, because a taller, more slender building is more flexible. Think of holding a ruler at one end and flicking the other. A short ruler barely moves, but a long ruler whips back and forth. Same principle. And the occupants of tall buildings are exquisitely sensitive to sway. Even very small movements, a fraction of an inch over a period of several seconds, can cause nausea, dizziness, and anxiety. It doesn't matter that the building is perfectly safe structurally. If the people inside feel like they're on a boat, they won't want to work there. And an unrentable building is an engineering failure no matter how structurally sound it is. So, how do engineers deal with this? Several ways, and they're all clever. The most fundamental approach is to make the building stiffer. Add more steel, use a different structural system, brace the frame more heavily. But this gets expensive and eventually counterproductive, because more steel means more weight, which means larger foundations, which costs even more. A more elegant approach is aerodynamic shaping. Instead of building a square box that catches wind like a wall, you sculpt the building's profile to reduce vortex shedding. Rounded corners, tapered profiles, notched setbacks, openings that let wind pass through. All of these can dramatically reduce wind-induced forces. The Taipei 101 Tower in Taiwan, for instance, has a stepped profile that disrupts vortex formation. The Shanghai Tower spirals as it rises, presenting a constantly changing profile to the wind that reduces the overall force by about 24% compared to a non-twisted design. The Burj Khalifa in Dubai, the tallest building in the world as of the mid-2020s, at 2,717 feet, has a Y-shaped cross-section that confuses the wind, preventing coherent vortices from forming. And then there's the most dramatic solution of all, tuned mass dampers. This is one of my favorite engineering concepts because it's so beautifully counterintuitive. You put a giant weight near the top of the building. We're talking hundreds of tons. And you mount it on bearings or pendulum cables so it can swing freely. When the building sways one way in the wind, the heavy mass swings the other way, absorbing the building's kinetic energy and converting it to heat through hydraulic dampers or friction brakes. It's like putting a heavy bowling ball inside a glass on a tray. When you tilt the tray, the bowling ball rolls to the other side and counteracts the tilt. The most famous tuned mass damper is probably the one in Taipei 101. It's a giant steel sphere, about 18 feet in diameter, weighing 730 tons, about the same as 100 elephants, suspended from cables between the 92nd and 87th floors. When a typhoon hits and the building starts to sway, the sphere swings in the opposite direction, reducing the building's movement by up to 40%. There are actually observation decks where visitors can watch the giant sphere swing during storms. It's one of the most mesmerizing things in engineering, this enormous golden ball, gently swaying back and forth in an enclosed space, quietly protecting the building and everyone in it. Now, we've been talking about what happens above the ground, but let me take you beneath the surface for a moment, because the part of a building you never see, the foundation, is often the most challenging engineering of all. And when I say challenging, I mean it. Building foundations for skyscrapers in places like New York, Chicago, Shanghai, or Dubai involves some of the most intense geotechnical engineering ever attempted. Here's the basic problem. A tall building is heavy. The Empire State Building weighs about 365,000 tons. That weight has to go somewhere. It flows down through the steel frame, through the columns, and eventually into the foundation. And the foundation has to spread that load into the ground without the building sinking, tilting, or settling unevenly. And the ground, unlike steel or concrete, is not a uniform, predictable material. It's a complicated, layered, variable, sometimes waterlogged mess of soil, clay, sand, gravel, and rock. And what it can support depends enormously on what type of ground it is and how deep you go. In Manhattan, skyscraper builders are blessed and cursed by the geology. Much of Midtown and Lower Manhattan sits on a layer of Manhattan schist, an incredibly hard metamorphic rock that's close to the surface. You can build directly on this rock, drilling into it and anchoring your foundations with rock bolts and massive concrete footings. This is why the skyline of Manhattan has two clusters of tall buildings, one downtown and one in Midtown, with a gap between them around Greenwich Village and Soho, where the schist dips deep underground and the soil above it can't support very tall buildings. At least, that's the traditional geological explanation. Some urban historians argue the gap has more to do with zoning and land use patterns than bedrock depth, but the geology certainly helps. In Chicago, there's no bedrock near the surface. The city sits on thick layers of soft clay, deposited by glaciers. You can't build on that clay. It would compress and settle unevenly under the weight of a tall building. So Chicago engineers pioneered a type of foundation called the caisson, which is basically a deep shaft sunk through the clay to the hardpan beneath, a denser, more compact layer of soil that can support more weight. They also developed the floating foundation, or mat foundation, which spreads the building's load over a very large area, like snowshoes spreading your weight so you don't sink into soft snow. And then there's the challenge of building in water-saturated ground, or in places with extremely weak soil. The Burj Khalifa in Dubai, for instance, sits on relatively weak sandstone and limestone. Its foundation consists of 194 concrete piles, each about 5 feet in diameter and about 150 feet long, driven deep into the ground. The friction between the piles and the surrounding soil supports the building's weight. It's called a friction pile foundation because the piles aren't resting on bedrock. They're held in place by the grip of the soil around them. The foundation also includes a massive concrete mat over 12 feet thick, covering a huge area, tying all the piles together and spreading the load. And there's one more foundation challenge worth mentioning, because it's one of the most dramatic in engineering. What do you do when the ground itself is trying to shake your building apart? Earthquakes. And the engineering response to earthquakes is so different from the engineering response to gravity and wind that it practically constitutes a separate discipline, because with gravity and wind, the forces are applied to the top and sides of the building and flow downward. With earthquakes, the force comes from below. The ground itself moves sideways, suddenly and violently, and the building has to cope with its foundation being yanked out from under it. Think about what happens during an earthquake. The ground moves horizontally, sometimes just a few inches, sometimes several feet, in rapid, violent pulses. The bottom of the building moves with the ground because it's attached to the ground. But the top of the building, thanks to inertia, Newton's first law, objects at rest tend to stay at rest. The top tries to stay where it was. So the building gets racked sideways, like pushing the bottom of a deck of cards while the top stays put. This creates enormous shearing forces in the structure, and if the building isn't designed to handle them, it collapses. Now, the simplest approach to earthquake resistance is brute strength. Make the building so strong and stiff that it can resist the shaking without deforming significantly. This works for shorter buildings, but for tall buildings, there's a subtler and more effective strategy. You make the building flexible. You let it sway with the earthquake rather than trying to resist it rigidly. Think of the difference between an oak tree and a willow in a windstorm. The oak is strong and rigid, but a sufficiently strong wind will snap its trunk. The willow bends, lets the wind pass, and springs back. The same principle applies to buildings. Japanese engineers have been pioneers in earthquake-resistant design for obvious reasons. Japan sits at the junction of 4 tectonic plates and experiences more significant earthquakes than almost any other developed country. The Japanese approach to seismic design has evolved over decades through painful experience. The 1923 Great Kanto earthquake destroyed much of Tokyo and Yokohama, killing over 100,000 people. The 1995 Kobe earthquake, despite decades of improved building codes, killed over 6,000 people and revealed weaknesses in even supposedly earthquake-resistant structures, particularly older buildings designed to earlier standards. One of the most remarkable innovations in earthquake engineering is base isolation. The idea is deceptively simple. Instead of bolting the building rigidly to its foundation, you put a layer of special bearings between the building and the ground. These bearings, typically rubber pads reinforced with layers of steel, or sometimes friction pendulum bearings, allow the foundation to slide sideways during an earthquake while the building above stays relatively stationary. The ground moves, but the building doesn't, because the bearings absorb the lateral motion. It's like putting your coffee cup on a tray with wheels. You can shake the tray back and forth, but the cup barely moves. The effectiveness is remarkable. Base-isolated buildings in Japan have come through major earthquakes with virtually no damage, while surrounding conventional buildings were severely damaged. Hospitals, data centers, museums with irreplaceable collections. These are prime candidates for base isolation, because even if a conventional building survives an earthquake structurally, the shaking can destroy equipment, topple shelves, break pipes, and render the building unusable for weeks or months. A base-isolated building stays calm inside while the ground goes crazy outside. But we've been spending a lot of time above the ground and just below it. Let me take you deeper, because some of the most impressive, most confusing, and honestly most terrifying engineering in human history happens underground. In tunnels, and tunneling is an entirely different beast from building bridges or skyscrapers, because when you dig a tunnel, you're not building on the ground, you're carving through it, removing the very material that's holding everything up, and hoping that what's left doesn't cave in on top of you. And the story of how humans learned to tunnel through rock, through sand, through clay, and even under rivers and oceans is one of the great sagas of engineering, and it starts with a man named Marc Isambard Brunel and a very ambitious, very dangerous hole under the River Thames. Marc Isambard Brunel, not to be confused with his more famous son, Isambard Kingdom Brunel, who we'll get to, was a French-born engineer who fled the French Revolution and eventually settled in England. He was one of those restless, inventive minds that the Industrial Revolution seemed to produce in abundance. He designed machinery for the Royal Navy, invented a mass production system for pulley blocks, the wooden blocks used in sailing ship rigging. That was one of the first true examples of machine-driven mass production. But the project that would consume nearly 2 decades of his life, nearly kill him, and eventually cement his reputation, was the Thames Tunnel. In the 1820s, London desperately needed a crossing under the Thames downstream of London Bridge. The river was too busy with shipping to build another bridge there, and the docks on both sides needed a connection for horse-drawn traffic. Several attempts had been made to dig a tunnel, and they'd all failed. The ground under the Thames at that point was waterlogged gravel and clay, saturated with river water. Every previous attempt had flooded, sometimes catastrophically. Brunel's approach was revolutionary. He invented a device called the tunneling shield, and the story of how he came up with it is one of those beautiful examples of engineering inspiration from nature. Brunel had been observing the shipworm, Teredo navalis, a marine mollusk that bores through wood. He noticed that the shipworm had a hard, ridged shell on its head that it used to grind through the timber, and as it moved forward, it secreted a smooth lining behind it, keeping the tunnel it had made from collapsing. Brunel's shield worked on the same principle. It was a massive iron framework, divided into 36 cells, each one big enough for a worker to stand in. The workers would excavate a few inches of soil from the face of the tunnel, then the entire shield would be pushed forward by jacks, and bricklayers behind the shield would line the newly exposed tunnel wall with bricks. The shield supported the face, preventing collapse. The bricks supported the tunnel behind. In theory, you could inch your way forward safely through the worst ground conditions imaginable. In theory. In practice, The Thames Tunnel was 18 years of hell. Construction began in 1825 and wasn't completed until 1843. The tunnel flooded 5 times. The first major flood, in 1827, nearly drowned the workers and filled the tunnel with river water and sewage. The Thames at that point was essentially an open sewer, and the tunnel had to be dug through ground that was saturated with it. The stench was indescribable. Workers regularly fell ill from the toxic gases, methane, hydrogen sulfide, that seeped from the contaminated ground. Marc Brunel himself suffered a stroke from the stress. His son, Isambard Kingdom Brunel, who served as assistant engineer, was nearly killed in the second major flood in January 1828, when the river broke through the tunnel face and swept several workers to their deaths. The young Brunel was pulled from the flood unconscious and barely survived. It took 7 months to pump out the water and seal the breach. The project ran out of money in 1828 and sat abandoned for 7 years, just a half-completed hole under the Thames, bricked up at both ends. It finally resumed in 1835 with government funding, and the tunnel was completed and opened to pedestrians in 1843. It was an engineering triumph, the first tunnel ever successfully driven under a navigable river, but it was never converted to horse-drawn traffic as originally planned, because the approach ramps were never built due to lack of funds. For years it served as a pedestrian tunnel, a tourist attraction, and eventually, some less savory purposes. It was finally incorporated into the railway system in 1865 and is still in use today as part of the London Overground network. If you ride the East London line between Rotherhithe and Wapping, you pass through Marc Brunel's tunnel, built nearly 2 centuries ago. Now, Brunel's tunneling shield was a brilliant concept, but it was a manual operation. Every bit of soil had to be dug out by hand. For the tunnels of the future, something faster was needed. And the machine that would transform tunneling forever, the tunnel boring machine, or TBM, would evolve gradually over the course of the 19th and 20th centuries into one of the most impressive pieces of engineering equipment ever built. A modern tunnel boring machine is, honestly, almost beyond description. It's a factory on wheels, contained inside a steel cylinder that can be over 50 feet in diameter. The front face is a rotating cutter head, a massive disc studded with cutting tools that grind away at the rock or soil face as it rotates. Behind the cutter head is a series of chambers and mechanisms, hydraulic jacks that push the machine forward, a system for removing the excavated material, called the muck, on conveyor belts or slurry pipelines, equipment for lining the tunnel with precast concrete segments as the machine advances, and all the support systems, ventilation, power, guidance systems, needed to keep the whole operation running. A large TBM can weigh over 7,000 tons and cost hundreds of millions of dollars, and they have names. TBMs are traditionally named, often after women or historical figures, and the naming ceremony is treated as a significant event. There's a superstition in tunneling that an unnamed TBM will bring bad luck. And here's what's really impressive about a modern TBM. It excavates, supports, and lines the tunnel in a single continuous operation. As the cutter head grinds forward, a ring of precast concrete segments, each one precisely manufactured to fit together like the pieces of a puzzle, is assembled behind the machine to form the permanent tunnel lining. The segments are erected by a mechanical arm inside the TBM, each ring pressed against the last, and the gaps are sealed with caulking and grout. By the time the TBM has passed through, the tunnel behind it is essentially complete, lined, sealed, and structurally sound. The machine leaves a finished product in its wake, and this technology made possible what might be the most ambitious tunneling project ever attempted. The Channel Tunnel, the Channel, linking England and France beneath the English Channel. The idea of a tunnel under the Channel had been proposed as early as 1802, when a French mining engineer named Albert Mathieu suggested a horse-drawn tunnel between the two countries. Napoleon apparently liked the idea. The British, who quite enjoyed having a moat between themselves and continental Europe, were less enthusiastic. The idea resurfaced repeatedly throughout the 19th and 20th centuries, and there were even some abortive attempts at digging. A tunnel was started from the English side in 1881 and got about a mile before the British government killed the project for defense reasons. But in the 1980s, political will and engineering capability finally converged. In 1986, British Prime Minister Margaret Thatcher and French President François Mitterrand signed the Canterbury Treaty, authorizing the tunnel's construction. The project was privately financed, no government money, which added enormous financial pressure to keep the project on schedule and budget. It was the largest privately funded engineering project in history at that time. The numbers are staggering. The tunnel is about 31 miles long, roughly 50 kilometers, of which about 23 miles are under the sea. Actually, there are 3 tunnels running parallel, 2 rail tunnels and a smaller service tunnel between them for ventilation, maintenance, and emergency evacuation. 11 TBMs were used, 6 from the French side and 5 from the English side, all digging toward each other and meeting in the middle. Think about that for a second. Imagine digging a tunnel from 2 countries simultaneously, under the English Channel, through chalk marl, a soft, chalky clay that's actually ideal for tunneling, and having the 2 ends meet up under the sea. The alignment had to be perfect. Laser guidance systems, satellite positioning, and incredibly precise surveying ensured that when the English and French tunnels met on December 1st, 1990, they were off by only about 20 inches horizontally and about 2 inches vertically. 2 inches. After digging for miles under the sea from opposite directions, the Channel Tunnel took about 6 years to build, employed over 13,000 workers, and cost about £4.65 billion, roughly double the original estimate, which is actually pretty typical for major infrastructure projects. 21% over budget in constant dollar terms, but double in nominal terms because of inflation and financing costs. The final breakthrough, when the service tunnel was connected, was celebrated by workers on both sides, the French crew and the English crew shaking hands through a hole in the chalk, deep under the English Channel. Trains now make the crossing in about 35 minutes. You can have breakfast in London and lunch in Paris. But here's the thing about tunneling that doesn't get talked about enough. It's not just about getting through the rock or soil. It's about managing water. Water is the tunneler's greatest enemy. Underground, you're constantly surrounded by groundwater, water filling the spaces between soil particles and the cracks in rock. And when you excavate a tunnel, you're removing the material that was holding that water in place. If the water pressure is high and the ground is permeable, water will flood into the tunnel face with terrifying force. Engineers deal with this in several ways. One is compressed air, pressurizing the space behind the cutter head to balance the water pressure outside, keeping the water at bay. This is the same principle Brunel used in his shield, and it's the same compressed air environment that gave the Brooklyn Bridge workers the bends. Modern TBMs use sophisticated pressurized systems, either compressed air or a slurry of bentonite clay, to maintain face pressure and prevent water ingress. Another method is ground freezing. You drill pipes into the ground around the planned tunnel alignment and circulate a refrigerant, brine or liquid nitrogen, that freezes the groundwater, turning the saturated soil into a solid, impervious mass. You can then tunnel through the frozen ground as if it were rock. It's expensive and energy-intensive, but for short, critical sections in very difficult ground conditions, it can be the only viable option. And then there's grouting, injecting cement, chemical resins, or other sealing materials into the ground ahead of the tunnel to fill the voids, solidify the soil, and reduce its permeability. Ground improvement, it's sometimes called. You're essentially modifying the earth itself, turning bad ground into good ground before you even start digging through it. All of these techniques, TBMs, compressed air, ground freezing, grouting, come together in the massive subway and utility tunnel projects happening in cities around the world right now. London's Crossrail project, now called the Elizabeth Line, bored over 26 miles of new tunnels under central London using 8 TBMs, some of them passing within a few feet of existing tunnels, building foundations, and buried utilities. The engineering precision required to thread a new tunnel through the underground spaghetti of an old city like London, without hitting the Northern Line, without cracking the foundations of historic buildings, without breaking a Victorian sewer, is almost incomprehensible. But let's come up for air. Let's talk about something completely different. Something that seems totally unrelated to bridges and tunnels and skyscrapers, but is actually connected by the same fundamental engineering principles we've been exploring all night. Let's talk about water. Specifically, let's talk about how water gets to your tap. Because the engineering that delivers clean water to billions of people every single day is, in many ways, the most important engineering in human history. More important than bridges, more important than skyscrapers, more important, arguably, than any other single feat of engineering, because without clean water, civilization simply doesn't exist. And the story of how we figured out how to move water, clean water, store water, and deliver it reliably to hundreds of millions of homes is a story of engineering genius, public health triumph, and a few spectacular disasters that shaped the modern world in ways most people never think about. Let's start with the most basic question. How do you move water? It sounds simple. Water flows downhill. Everyone knows that. But here's the thing. The places where people live aren't always below the places where the water is. And even when they are, getting water to flow downhill in a controlled, reliable, and sanitary way over distances of miles or even hundreds of miles is one of the great engineering challenges of civilization. The Romans understood this better than anyone before them, and arguably better than anyone for the next 1,500 years. Roman aqueducts are among the most famous engineering structures in history, and for good reason. The city of Rome at its peak, around the 2nd century CE, had a population of over 1 million people, and it was served by 11 major aqueducts that delivered an estimated 1.3 billion liters of fresh water per day. That's about 300 gallons per person per day, which is actually comparable to modern American per capita water usage. And they did it entirely with gravity. No pumps, no engines, just water flowing downhill, through channels, tunnels, bridges, and pipes, from mountain springs and rivers to the heart of the city. The engineering of a Roman aqueduct is subtle and fascinating. The gradient, the downward slope, had to be incredibly precise. Too steep and the water would flow too fast, eroding the channel. Too shallow and the water would barely move, or silt would accumulate and block the channel. The typical gradient was about 1 in 5,000, meaning the channel dropped about 1 foot for every 5,000 feet of horizontal distance. That's roughly 2 inches per 100 feet. Over a distance of 60 miles, that's a total drop of only about 60 feet. And the Romans maintained that gradient consistently, over mountains, through valleys, across rivers, mile after mile, using nothing but plumb bobs, water levels, and the groma, a simple sighting instrument for establishing straight lines and right angles. When the aqueduct had to cross a valley, they built the famous multi-tiered arcades, rows of arches stacked on top of each other, carrying the water channel at the required elevation. The Pont du Gard in southern France, built around 19 BCE, is a stunning example. 3 tiers of arches, 160 feet tall, carrying an aqueduct channel across the Gardon River Valley. The channel at the top drops only about 1 inch per 100 feet over its 31-mile length from the spring at Uzès to the city of Nîmes. That's an astonishing degree of precision for any era. When the aqueduct encountered a hill, the Romans would tunnel through it. When it had to descend into a valley and climb up the other side, they sometimes used an inverted siphon, a sealed pipe that drops down into the valley and climbs up the far side, with the water driven upward by the pressure of the water behind it, just like water flowing through a U-shaped tube. The Romans built siphon pipes out of lead and stone, and the pressures involved were enormous. Some Roman siphons had to withstand pressures equivalent to a 10-story head of water. Lead pipe, by the way, the Latin word for lead is plumbum, which is where we get the words plumbing and plumber. But the Romans, for all their brilliance in water transport, didn't understand water purification the way we do today. Their water was clean, mostly because the sources were clean, mountain springs and rivers upstream of major settlement. They used settling basins to remove sediment, but they didn't treat the water chemically. They didn't need to, because the water wasn't contaminated at the source. But as cities grew, as populations concentrated, and as sources of clean water became scarce, the question of water purity would become the single most important public health issue in human history. And the person who cracked that problem open, who proved the connection between contaminated water and deadly disease, did so in the most dramatic way imaginable, during a cholera outbreak in the crowded streets of Victorian London. His name was John Snow, and his detective work in the summer of 1854 is one of the great stories of engineering, science, and public health coming together to save lives. Cholera was the terror of 19th-century cities. It killed with horrifying speed. A person could be perfectly healthy in the morning and dead by nightfall. The symptoms were ghastly: violent vomiting, catastrophic diarrhea, dehydration so severe that the skin turned blue and collapsed. London suffered multiple cholera epidemics through the 1830s, 40s, and 50s, each one killing thousands, and nobody knew what caused it. The prevailing theory was miasma, bad air, the stench of the city, the rotting garbage, the open cesspools. These noxious smells were believed to carry the disease. It seemed to make sense. Cholera struck hardest in the dirtiest, smelliest parts of the city. John Snow disagreed. Snow was a physician, a meticulous observer, and one of the pioneers of anesthesia. He had administered chloroform to Queen Victoria during childbirth. But his real passion was epidemiology, the study of how diseases spread through populations. And he'd been studying cholera for years, building an evidence case that the disease was transmitted not through air, but through water, specifically through water contaminated with the sewage of cholera victims. In the summer of 1854, a devastating cholera outbreak struck the Soho district of London. Over 600 people died in a matter of weeks. Snow investigated, going door to door, mapping every case, noting which water pump each victim had used, and the pattern was unmistakable. The cases clustered around a single water pump on Broad Street, now Broadwick Street. People who drank from that pump got sick. People who didn't, mostly didn't. There was even a brewery nearby whose workers were largely spared, because the brewery had its own private well, and the workers drank beer rather than water. Snow presented his findings to the local authorities and persuaded them to remove the handle from the Broad Street pump, making it unusable. The outbreak was already declining by then. Many residents had fled the area, but the removal of the pump handle became one of the most famous symbolic moments in public health history. Snow's map of the cholera cases, with each death marked as a dot clustering around the pump, is considered one of the founding documents of epidemiology. But here's what's important for our engineering story. Snow proved that contaminated water kills people. He proved that the water supply and the sewage system cannot mix. And that insight, that clean water and waste must be kept absolutely, rigorously separate, drove the engineering revolution that would transform cities over the following decades. Because once you understand that sewage in the water supply causes deadly disease, you have no choice. You have to build systems to keep them apart. And building those systems, the water treatment plants, the distribution networks, the sewage collection systems, the wastewater treatment facilities, is some of the most consequential engineering ever performed. And the person who led the charge in London, the person who built the sewer system that would become the model for cities around the world, was an engineer named Joseph Bazalgette. He's not a household name the way Brunel is, but there's a reasonable argument that Joseph Bazalgette saved more lives than any other engineer in history. In the 1850s, London was drowning in its own waste. Over 2 million people were producing sewage that flowed through open drains, cesspools, and ditches directly into the Thames, which was also the source of much of the city's drinking water. The smell was so bad that in the summer of 1858, the year that became known as the Great Stink, the stench from the Thames was so overwhelming that Parliament, whose building sits right on the river, could barely function. Legislators held handkerchiefs to their faces. The curtains in the House of Commons were soaked in lime chloride to try to mask the smell. That summer, Parliament authorized Bazalgette's plan for a comprehensive sewer system, simply because they couldn't stand the smell anymore. One of the most important public works projects in history was motivated, in the end, not by scientific understanding, but by the fact that politicians couldn't breathe. Bazalgette's system was a masterpiece of civil engineering. He designed over 1,000 miles of street sewers, feeding into 82 miles of main intercepting sewers, large brick tunnels that ran along the embankments of the Thames, intercepting the sewage before it reached the river and carrying it downstream to treatment works east of the city. The system was built to handle not just current needs but future growth. Bazalgette famously doubled the diameter of the pipes from what his initial calculations suggested, saying, "We're only going to do this once, and there's always the unforeseen." That decision to overbuild turned out to be one of the most prescient in engineering history. London's population more than doubled over the following decades, and Bazalgette's sewers handled the load. The intercepting sewers are still in use today, more than 150 years after they were built. They run beneath the Victoria Embankment, the Chelsea Embankment, and the Albert Embankment, the grand riverside promenades that Bazalgette also designed to run on top of his sewers, reclaiming land from the Thames in the process. He literally reshaped the geography of London while building its sanitary infrastructure. And what Bazalgette did for London, engineers in cities around the world did over the following decades: Paris, Berlin, New York, Chicago. All built comprehensive sewer systems in the late 19th and early 20th centuries. The death rates from waterborne diseases plummeted. Cholera, typhoid fever, dysentery, diseases that had killed hundreds of thousands, became rare in cities with modern water and sewage systems. It's been argued, persuasively, that the civil engineer's contribution to public health through clean water and sanitation has saved more lives than any medical advance in history, including antibiotics and vaccines. And the modern water treatment plant is itself a marvel of engineering, though you'd never think of it that way because it's so invisible. When you turn on your tap, you probably don't think about what happened to the water before it got there. But here's the short version. Raw water is drawn from a river, lake, or reservoir. It first goes through screening to remove large debris, sticks, leaves, fish. Then it enters a coagulation and flocculation stage, where chemicals, typically aluminum sulfate or iron salts, are added to make tiny suspended particles clump together into larger particles called floc. The floc settles out in a sedimentation basin. The water then passes through filters, layers of sand, gravel, and sometimes activated carbon that remove remaining particles and some dissolved contaminants. Finally, it's disinfected, usually with chlorine or chloramine, to kill bacteria and viruses. The result is water that's safe to drink, reliably, consistently, at the turn of a handle. And the engineering challenge isn't just treatment, it's distribution. Getting treated water from the treatment plant to every home, every office, every school, every hospital, every fire hydrant in a city of millions requires a network of pipes, pumps, valves, and storage tanks of staggering complexity. New York City's water distribution system, for instance, includes over 6,800 miles of water mains, over 100,000 valves, and over 100,000 fire hydrants. The water is delivered at a pressure of about 40 to 80 pounds per square inch, enough to push it up to the 6th floor of most buildings. Above that, buildings need their own pumps and rooftop tanks. Those water towers you see on the roofs of New York apartment buildings, they're not decorative, they're part of the engineering. Water is pumped up to the tank, and gravity feeds it down to the upper floors. Now, let me take a sharp turn here, because there's one more area of engineering that I really want to talk about tonight. One that affects your life probably more often than bridges or tunnels or even water pipes, and it's the one that seems to puzzle people the most. How do airplanes fly? How does a machine weighing hundreds of tons lift itself off the ground and stay in the air for hours? It seems impossible. It seems like it shouldn't work. And the story of how we figured it out is one of the most human, most dramatic, most surprising stories in all of engineering. And it starts not with the Wright brothers, though we'll get to them, but with a fundamental misunderstanding about flight that persisted for centuries, and with a physical principle that most people, even today, get wrong. It starts with a question that has a much more interesting answer than most textbooks tell you. How does a wing actually create lift? So here's how a lot of people explain it, and here's why that explanation is mostly wrong. You might have heard this version in school. A wing is curved on top and flat on the bottom. When air flows over the wing, the air going over the curved top has to travel a longer path than the air going under the flat bottom. And because the air that went over the top and the air that went under the bottom have to rejoin at the back of the wing at the same time, they have to meet up again. The air on top has to move faster to cover the longer distance, and faster moving air has lower pressure, according to Bernoulli's principle. So the pressure on top of the wing is lower than the pressure on the bottom, and this pressure difference pushes the wing upward. That's lift. Clean, simple, elegant, and wrong. Or at least, very misleading. There are several problems with this explanation, and they matter because they obscure what's actually happening, which is more interesting and more beautiful than the simplified version. First, the idea that the air over the top and the air under the bottom have to meet up at the trailing edge at the same time, what's sometimes called the equal transit time theory, has no physical basis. There's no law of physics that says two parcels of air split by a wing must reunite at the back. And in fact, they don't. Experiments and computer simulations show that the air going over the top of the wing reaches the trailing edge well before the air going under the bottom. The air on top moves much faster than the equal transit time theory predicts. Second, many wings aren't even curved on top and flat on the bottom. A symmetric airfoil, one that's the same shape on top and bottom, can still generate lift as long as it's tilted at an angle to the airflow. This angle is called the angle of attack, and stunt planes fly upside down, which would be impossible if lift depended entirely on the shape of the wing. So what actually creates lift? Here's the real story, and it's simpler in some ways and more subtle in others. When a wing moves through the air, or equivalently, when air flows over a wing, the wing deflects the air downward. That's it. That's the fundamental mechanism. The wing pushes air down, and by Newton's third law, every action has an equal and opposite reaction. The air pushes the wing up. That upward push is lift. Now, how does the wing push air down? Partly through the bottom surface, which is tilted into the airflow and simply shoves the air downward like a ramp. But the top surface is even more important, and here's where it gets interesting. When air flows over the curved top of the wing, it follows the curve of the surface. This is called the Coanda effect, the tendency of a fluid stream to follow a curved surface rather than continuing in a straight line. As the air curves downward following the top of the wing, it's being accelerated. Its direction is changing, which means it's accelerating, even if its speed stayed constant. And an accelerating flow requires a pressure difference to drive it. The pressure above the curving air has to be higher than the pressure below it to push the air into the curve. This means the pressure right at the surface of the wing, on top, is reduced, and that reduced pressure on top, combined with the higher pressure on the bottom, creates a net upward force, lift. So Bernoulli's principle is involved. There really is lower pressure on top and higher pressure on the bottom, but it's not because of equal transit times. It's because the wing is redirecting the airflow downward, and the physics of that redirection create the pressure difference. Newton and Bernoulli aren't competing explanations. They're two descriptions of the same underlying physics, viewed from different angles. Newton focuses on the momentum of the air being deflected. Bernoulli focuses on the pressure distribution around the wing. Both are correct. Both are incomplete by themselves. And understanding this, really understanding how a wing generates lift, was one of the key engineering breakthroughs that made powered flight possible. Because it meant you could design wings systematically. You could test different shapes, different angles of attack, different airfoil profiles, and predict how much lift they'd generate at a given speed. And the people who first put this understanding to practical use, who built the first heavier-than-air-powered aircraft that actually flew, were two bicycle mechanics from Dayton, Ohio, who had no college degrees, no funding, and no support from the scientific establishment, Wilbur and Orville Wright. And the Wright brothers' story is often told as a tale of plucky amateurs beating the experts, but that undersells them dramatically. They weren't amateurs. They were extraordinarily rigorous, methodical engineers who outperformed everyone else in the field because they were smarter about identifying the real problems. In the 1890s, several well-funded groups were trying to build flying machines. The most prominent was Samuel Langley, secretary of the Smithsonian Institution, who had a $50,000 grant from the War Department, an enormous sum at the time, and a team of skilled engineers. Langley built a large, steam-powered aircraft called the aerodrome, tested it over the Potomac River, and twice, in October and December 1903, watched it crash ignominiously into the water, seconds after launch. The problem was control. Langley had focused on building an engine powerful enough to keep the machine aloft, but hadn't solved the problem of how the pilot would actually steer the thing. The Wrights saw the problem more clearly. They realized that the key challenges of flight were not, as most people assumed, a matter of getting enough power. The key challenges were lift, control, and stability, and they attacked them in order, methodically, over several years. First, they researched everything that had been published about flight. They read Octave Chanut's surveys, Langley's papers, Otto Lilienthal's data on wing shapes, and they discovered something disturbing. Much of the published data on lift coefficients, the numbers that tell you how much lift a given wing shape produces at a given speed, was wrong. Lilienthal's tables, which were widely used and trusted, gave values that the Wrights couldn't reproduce. So in 1901, they built their own wind tunnel, a simple wooden box about 6 feet long with a fan at one end, and systematically tested over 200 different wing shapes, recording lift and drag for each one. They generated the most accurate aerodynamic data in the world, in their bicycle shop, with equipment that cost almost nothing. Then they tackled control, and this was their real breakthrough. Most other experimenters tried to make their aircraft inherently stable, designed to resist disturbances and return to level flight on their own, like a ball at the bottom of a bowl. The Wrights took the opposite approach. They designed their aircraft to be inherently unstable, like a ball balanced on top of a hill, and they gave the pilot active control to keep it balanced. Their key innovation was wing warping, a system of cables and pulleys that allowed the pilot to twist the wings, increasing the angle of attack on one side and decreasing it on the other. This created more lift on one wing and less on the other, allowing the aircraft to bank and turn. It was the precursor to the ailerons used on every airplane today. They combined this with an elevator at the front for pitch control, nose up and nose down, and a rudder at the back for yaw control, turning left and right. 3 axes of control, all managed by the pilot. Nobody else had put all 3 together in a workable system. The Wrights did, and they practiced for years with unpowered gliders at Kitty Hawk, North Carolina, a remote strip of sand dunes chosen for its steady winds and soft landings, refining their control system until they could fly the glider reliably and predictably. And then, only after they had the aerodynamics and the control system worked out, did they tackle the engine. They needed an engine that was light enough and powerful enough to get their aircraft off the ground. Nothing available met their specifications, so they designed and built their own gasoline engine with the help of their bicycle shop mechanic, Charlie Taylor. The engine weighed about 180 pounds and produced about 12 horsepower, a power-to-weight ratio better than anything else available at the time. They also designed their own propellers, using their wind tunnel data, treating the propeller as a rotating wing and applying the same aerodynamic principles. Their propellers turned out to be about 66% efficient, which was remarkably good for first-try propellers, designed from theory rather than trial and error. On December 17, 1903, at Kill Devil Hills near Kitty Hawk, they flew. The first flight, with Orville at the controls, lasted 12 seconds and covered 120 feet, less than the wingspan of a modern 747, but it was genuine powered, controlled, sustained heavier-than-air flight. They made 4 flights that day, the longest lasting 59 seconds and covering 852 feet, and then a gust of wind caught the aircraft on the ground and tumbled it, damaging it beyond easy repair. But it didn't matter. They'd done it. They'd solved the problem that had obsessed humanity for centuries. And what's remarkable, what's almost poignant, is how little attention it got at the time. The Wrights were secretive about their achievement, partly because they were still refining the design, and partly because they were trying to secure patents before competitors could copy them. The press, barely covered it. The Smithsonian, embarrassed by Langley's failure, was slow to acknowledge the right's success. It took years for the world to fully recognize what had happened on that December morning in North Carolina. But once aviation took off, and it took off fast, the engineering challenges multiplied enormously. Building a flimsy biplane that could carry one person for a minute was one thing. Building an aircraft that could carry dozens of passengers hundreds of miles in comfort and safety was something else entirely. And the evolution from the Wright Flyer to the modern airliner is a story of constant engineering innovation, punctuated by some devastating failures that taught the profession lessons written in tragedy. And one of the most significant of those lessons involves a concept that's fundamental to engineering, but that most people have never heard of. A concept that explains why things that seem perfectly strong can suddenly, catastrophically, without warning, break. A concept that has killed thousands of people and that drives some of the most important engineering analysis done today. It's called metal fatigue. And the story of how we discovered it, the hard way, starts with a beautiful, sleek, revolutionary British jet airliner called the de Havilland Comet, and a series of disasters in the early 1950s that shook the aviation industry to its core. The de Havilland Comet was a marvel. It entered service with BOAC, the British Overseas Airways Corporation, the predecessor of British Airways, in May 1952, and it was the world's first commercial jet airliner. It was gorgeous, sleek, streamlined, with its 4 ghost turbojet engines buried cleanly inside the wing roots. It flew higher and faster than any propeller-driven airliner, cruising at over 450 miles per hour at 40,000 feet. Passengers loved it. The ride was smooth, the noise was lower than propeller aircraft, and the speed was exhilarating. Britain was immensely proud. The Comet was a symbol of post-war British engineering excellence, proof that Britain was still a technological leader. And then, on January 10, 1954, a BOAC Comet, Flight 781 from Rome to London, broke apart in mid-air over the Mediterranean Sea near the island of Elba. All 35 people on board were killed. The aircraft had simply disintegrated at cruising altitude, with no warning, no distress call. Wreckage and bodies fell into the sea. The Comet fleet was grounded while investigators tried to determine the cause. After modifications and inspections, the fleet returned to service. And then, on April 8, 1954, less than 3 months later, another BOAC Comet, Flight 7883, broke apart in mid-air over the Mediterranean near Naples. 21 people killed. Again, no warning. The aircraft tore itself apart at altitude. The Comets were grounded permanently. What followed was one of the most intensive engineering investigations ever conducted. The Royal Aircraft Establishment at Farnborough led the inquiry. They recovered as much wreckage as possible from the Mediterranean, painstakingly reassembling the fuselage structure, piece by piece on a framework, like a 3-dimensional jigsaw puzzle. And they ran a brilliant, grueling experiment. They took a complete Comet fuselage, placed it in a massive water tank, and subjected it to repeated pressurization cycles, simulating the inflation and deflation of the cabin that happens on every flight as the aircraft climbs to altitude and descends again. Each time the plane goes up, the cabin is pressurized. The air inside is kept at a breathable pressure, while the air outside, at 40,000 feet, is almost a vacuum. The cabin swells slightly, like a balloon. When the plane descends, it deflates. Up, down, swell, shrink. Every single flight. The test fuselage failed after the equivalent of about 9,000 flights. And when the investigators examined where it failed, they found something that would reshape the entire field of structural engineering. The fuselage had cracked. a fatigue crack, starting from the corner of a window, specifically from a rivet hole at the corner of one of the rectangular cabin windows. Here's what happened, and here's why it matters so much. Metal fatigue is a phenomenon where a material fails, not because the stress exceeds its breaking strength, but because repeated cycles of stress, each one well below the breaking point, gradually create and grow tiny cracks. Think of bending a paperclip back and forth. Each individual bend doesn't break it. The force you're applying is way below what would be needed to snap the wire in a single pull. But bend it back and forth enough times and it breaks. That's fatigue. The repeated flexing creates microscopic cracks at points of stress concentration, and each cycle makes the cracks grow a little longer, until eventually the remaining material can't carry the load and the whole thing fails, suddenly and catastrophically, without any visible warning. And the comet's square window corners were the problem. A sharp corner in a structure is a stress concentrator. The stresses at that point are much higher than the average stress in the surrounding material, because the forces flowing through the material have to make a sharp turn at the corner, and they pile up there. It's like water flowing through a pipe. If the pipe has a sharp bend, the pressure increases at the bend. In the comet's fuselage, every time the cabin pressurized, the skin stretched, and the stresses concentrated at the window corners. Each pressurization cycle was well within the design limits. Each individual cycle was perfectly safe. But after thousands of cycles, fatigue cracks initiated at those stress concentrations grew silently, invisibly, through the aluminum skin, and eventually reached a critical length where the fuselage ripped open explosively. The lessons from the comet disasters transformed aviation engineering. Square windows in pressurized aircraft were replaced by oval or round windows. Round shapes eliminate sharp corners and spread the stresses much more evenly. Every subsequent commercial aircraft design incorporates fatigue analysis as a central element. Engineers calculate how many pressurization cycles the fuselage can withstand before fatigue becomes a risk, and they set maintenance inspection schedules well before that point. Aircraft are designed with fail-safe and damage-tolerant structures, multiple load paths, so that if one component cracks, the load is carried by neighboring components, and the crack can be detected during maintenance before it reaches a critical size. And metal fatigue isn't just an aviation issue, it's everywhere. Bridge components, offshore oil platforms, pressure vessels, medical implants, automotive suspension parts, helicopter rotors, ship hulls. Anything that experiences repeated loading is susceptible to fatigue. The comet disasters just made the whole engineering profession confront the phenomenon in a way they hadn't before. Here's something that ties this back to a story we told much earlier. Remember the Roeblings and the Brooklyn Bridge? One of the reasons that bridge has lasted so long, one of the reasons it's still carrying traffic over 140 years after it opened, is that John Roebling massively overbuilt it. His safety factors were enormous, far larger than modern engineering practice would require. He used roughly 6 times more steel than was strictly necessary. He did this because he didn't fully trust the new material, because he wanted to be absolutely certain the bridge would stand. And that overbuilding, that generous margin of safety, means the bridge has enormous reserves to accommodate the fatigue damage, the corrosion, the increased traffic loads that Roebling never anticipated. His conservatism, his caution, his unwillingness to cut corners, that's what gave the bridge its longevity. And that's a principle that runs through the entire history of engineering. Safety factors, margins of error, building stronger than you think you need to, because the universe is full of surprises, loads you didn't predict, materials that behave differently than you expected, conditions you never imagined. and the only thing standing between the people who use your structure and disaster is the margin of safety you built in. The Tacoma Narrows Bridge failed, partly because its designer pushed for elegance and slenderness at the expense of margin. The Brooklyn Bridge survived, partly because its designer insisted on massive overstrength. Neither extreme is ideal. Overbuilding is wasteful and expensive, while underbuilding is dangerous. But the history of engineering is very clear about which direction is safer to err. And this brings us, in a way, to the bigger picture. Because engineering, at its core, is really about one thing: managing uncertainty. Engineers don't build in a world of perfect knowledge. They build in a world of approximation, estimation, assumption, and judgment. They don't know exactly what loads the building will face. They don't know exactly how strong the steel is. There's always some variation. They don't know exactly what the soil conditions are, or how the climate will change, or what mistakes might be made during construction. Engineering is the art of making things work despite not knowing everything. And the tools engineers use, safety factors, redundancy, testing, inspection, codes, and standards, are all ways of coping with that fundamental uncertainty. The building codes that govern construction today are fascinating documents, though nobody except engineers would describe them that way. They represent accumulated wisdom from centuries of building and failing and building again. Every clause, every requirement, every number in a building code has a story behind it, usually a story of failure. The fire codes exist because of the Great Chicago Fire of 1871 and the Triangle Shirtwaist Factory Fire of 1911, where 146 garment workers died because the exit doors were locked. The seismic provisions exist because of the San Francisco earthquake of 1906, the Kobe earthquake of 1995, the Northridge earthquake of 1994. The wind loading requirements exist because of the Tacoma Narrows Bridge and the damage from hurricanes and tornadoes over generations. Every line in those codes was paid for, often in lives. And today, engineers have tools that their predecessors couldn't have imagined. Computer simulation, finite element analysis, allows engineers to model the behavior of a structure under any conceivable loading condition, dividing the structure into thousands or millions of tiny elements, and calculating the stresses and deformations in each one. What used to take months of hand calculation can now be done in hours on a desktop computer. Wind tunnel testing has been augmented by computational fluid dynamics, which can simulate airflow around structures with remarkable accuracy. Materials science has given us alloys, composites, fiber-reinforced polymers, high-performance concrete, materials with properties tailored precisely to the demands of the application. But here's what hasn't changed, and what will never change. The fundamental challenge of engineering is still the same one it was 5,000 years ago, when someone looked at a pile of stone blocks and imagined a pyramid. It's the challenge of understanding forces, how they flow, how materials resist them, how shapes channel them. It's the challenge of understanding materials, how they stretch and compress and bend and fatigue and corrode and fail. It's the challenge of understanding risk, what might go wrong, how likely it is, and what happens if it does. And above all, it's the challenge of building things that serve people, that keep them safe, that connect them, that carry them over rivers and through mountains and into the sky. Every bridge you cross, every building you enter, every tunnel you drive through, every glass of water you drink from a tap, every flight you board, behind each one is an engineering story. A story of people who understood forces and materials and shapes, who calculated and tested, and sometimes guessed, who got it right more often than they got it wrong, and who learned from every failure. The buildings are not just concrete and steel, They're the accumulated understanding of thousands of years of people pushing against the limits of what's possible, failing, learning, and pushing again. And that's a comforting thought, actually, as you lie there. The structure around you, the walls, the roof, the floor, is the product of all that accumulated knowledge. Every nail was placed by someone who understood, at some level, the forces that nail would carry. Every beam was sized by an engineer who calculated the loads, the stresses, the deflections, and added a safety factor to cover the things they couldn't predict. The building code that governs your home or your apartment is a document soaked in the lessons of history, every provision tested by time. So let that weight settle. Let the bed hold you. The forces are in balance. The compression and the tension are doing their quiet work, just as they've been doing since the first stone was placed on top of another stone, thousands of years ago, by someone who noticed that wide bases hold heavy loads, that arches carry weight and compression, that triangles are rigid, that water flows downhill, that wings deflect air downward, that metal bends before it breaks, that the universe has rules, and that those rules, once understood, can be used to build the most extraordinary things. The engineers who figured all this out, the Brunels and the Roeblings and the Bazalgettes and the Wrights, the Roman builders whose names we'll never know, the Egyptian workers who stacked those impossible stones, the anonymous craftspeople who built the first arch, the first truss, the first dam, they're all part of the same story. Your story. The story of a species that looked at the world and said, I can make this better. I can span this river. I can shelter these people. I can move this water. I can lift this weight. And they did. Every day, in every city, in every structure you'll ever enter, they're still doing it. The forces are still flowing. The materials are still holding. The engineering is still working. Quietly, reliably, invisibly, keeping you safe, keeping the roof up and the water clean, and the bridge standing, and the plane aloft, all night, while you sleep. It just keeps working, and it will still be working in the morning. So let the engineering carry you now the way it carries everything else, steadily, patiently, with margins to spare. The arches are holding. The cables are taut, the foundations are firm. And you, lying here in the quiet, held up by the accumulated genius of 100 generations of builders, you can let go. The structure is sound. Everything is in equilibrium, and sleep, when it comes, is just another kind of balance. Settle into it. The engineers have done their work. The rest is easy.